Hello, CSC and ISC students of 5th semester. Welcome to Automata Theory and Computability 7th lecture. We have come to the last session of this module 1. This module 1 today will be covering the whatever is remaining in chapter 5 and also in chapter 4 and 3. So, I have taken that order because that is more meaningful, because you have to study the chapter 3 in the end. So, that a lot of concepts are there. So, that will be made clear. So, we will go in the order of 3, 5, 4 and 3. So, today very little is left in the chapter 5, that is finite state transducers. We will see in that Moore and Mealy machines, and also I will tell you what is a bidirectional transducers. These are not bidirectional. Moore and Mealy are not bidirectional. Then bidirectional transducers also can be constructed. Then chapter 4 will be dealing with computation. What is can be computed, and for that what is the pre-requirement for that, and what are the some of the new functions. We have seen some of the functions earlier. If you recollect, the functions that can be operated on languages are union, intersection, because language is a set. So, all the set operations can be applied. Here we are going to see some more functions, and again all the time when our intention is, when we apply functions, is it closed under that operation. So, we will see some new operations and thing. Then finally, in the chapter 3 is a concluding chapter, wherein we will be defining the framework for defining the language. Then afterwards, we will see the very important outcome of this automata theory and computability, that is hierarchy of language classes. That is a very important outcome, which should which should give you a very important background for the further study. Now, what is a first Moore machine is a transducer. What is transducer? You can see the definition that it converts the variations in physical quantity such as pressure, brightness into electrical signals. This you have come across every day. See, for example, your speaker is there. You speak, vibrations will go into the speaker and they will all be converted into electrical signals and transmitted. So, transducer is such a device. Then how it is connected to Moore machine, we will see. So, that means it takes some input. If you abstract the transducer, it takes some input in one form and gives it in some other form. So, that is what the Moore machine is going to do. First, we will see the definition of the Moore machine. It's like it is also a discrete finite state machine, but it has got, instead of 5 parameters, it has got 7 parameters are there. As you know, K is a finite set of states, sigma is the alphabet set. Then we have O, that is output alphabet, delta is a transition function, D is the display or the output function, then S is the state, that is start state. What is the start state? A is a subset of K, a set of accepting states. So, I have written it not important, because in this problem you will not see the importance of a final state in case of Moore machine, like in deterministic finite state machines what we have studied earlier, or in the non-deterministic finite state machines also we have seen, where the finite accepting state is a very important concept, but that may not play a very important role in case of Moore machine. So, Moore machine is for something else. So, it has got a input and you will see that this is the output. So, that is like a acts like a transducer. So, I have taken an example, simple example, and there is an example in the book which you should follow it, and this is a very simple example of a Moore machine. in Moore machine, each state is associated with the output. The state is associated in the previously we never had the concept of an output. It was only either the given input string is accepted or it is not accepted. Now, accepted means it should reach final state, then it is accepted. If it does not reach accepting state, then it is rejected. So, this was the way it was used. Now, here each state outputs certain things. What is that? Why it is useful and all that. Suppose we want to a Moore machine to output 0 when the length of the input string is even. See, we have written the finite state machine for the accepting all the even length strings. We have done that problem. Okay. So, here if it is even length, it should output 0, otherwise it should output 1. Sigma is a comma b. So, it is a very simple problem, wherein suppose if it is epsilon is even, then that state should output 0. Now, for example, AA, it will reach 0, that means AA is even, therefore, it should output 0. For example, it is only B, it reaches 2, then it is not a even, so it should output 1. So, if you run around any number of times, even means it will reach state 1, which is accepting state, but in this case it is not important. So, it will output 0, and if it is a odd number, the length of the input string is odd number, it will reach 1 and it will output 1. So, this may not be a thing unless you write a transition diagram for this, it may not be clear. Now, the transition diagram for this will be like this. So, transition function, it is in 1. So, either on A or B it will go to 2. Then in the state 1 is associated with 0. As long as the state, when it is in state 1, if epsilon is there or even number of strings are there. So, when you input A, it will go to 2. So, what is associated with the 2 is 1. So, that means when it is odd length, then it will be 1, if it is even length, it will be 0. So, this is it takes certain input and gives output. So, therefore, acts like a transducer, that is why it is a Moore machine is called a transducer. There is one more machine called Mealy machine. This also acts as a transducer. There is a slight difference between the Moore machine and a Mealy machine. As we have seen already, the Moore machine, each state is associated with a output, whereas in the case of Mealy machine, each input is associated with some output. So, that is the difference. So, here we require only 6 tuples for defining the Mealy machine. Okay. As usual, K is the finite set of states, sigma is the input alphabet, O is the output alphabet, then S is the start state as usual, A is a subset of K, that is accepting state. Again I want to emphasize here, it will be confusing, it is not important here in this case. So, delta is a transition function, it maps K into sigma to K into output star. Okay. So, output is associated with each input. So, this again we will take a simple example. This is not worked out in the book, I have taken some other book. So, you will have 2 examples for each one of them. Now, the example for Mealy machine. Okay. So, now what is that we want to think, that is L is a language derived from A comma B star. So, what is the what strings will be in L? All the things that end in AA or BB. Okay. So, in the beginning what it comes is not important. Does it end in AA or does it end in BB? It is what is the requirement. Requirements are input ends in AA or BB, then it will reach the as usual final state. So, AA or BB is there, then the output should be Y, otherwise it should have output no. That means to say that when you output simple A, it should be no, yes or no. The output alphabet is yes or no, y or n. Okay, you can take that as yes or no. See, for example, if we input, you are in the start state A, you would the output immediately output will be n, because it does not end in AA. Suppose you are here in the second state, and if you input one more A, then immediately it is ended in AA. So, output will be y. Suppose you output one more input one more A, then what happens again, it is not ending in this thing. So, any number of A will be here only, that is any number of A's is as good as ending in A. So, it will be always output y only. For example, if you input B, then it is not ending in BB, only single B has come, therefore, no will come. Now, if you have one more B, then it is BB. Any number of B's will go on outputting y, because that is as good as ending in BB. So, if initially if you have B, then it will be single B is there, it will output n. So, what is that you see here? I want to represent that diagrammatically like this. I will take some representative A, B, A, B, B, A. If this is the input, then how the output will look like that. So, when you see A, then it will go to 2 and it will output n. Then from 2, when you say input, then it will go to state 3. If you want, you can write the state. So, on n A, it will go to 2. 2 on B will go to 2 on B, it will go to 3, state 3, and again it will be n. Then when you are in third state, then if you have a, then it will go to 2 and again it will be it will go to 2 and again it will be n. Then when you are in state 2, again input is A, then it will be y, and it will be remain in state 2. So, you see that only when there are 2 consecutive A's are there, then only the output will be y. Otherwise, all the time it is going to be a thing. I will complete this. Then suppose you are in state 2 now, state 2, and if the B comes, in state 2 B comes with, it will go to state 3. And what is the output associated with the thing? N, because it is not this thing. Now, in state 3, again B comes, means you will be in state 3 only, and the output is y. Yes. Okay. Then again you are in state 3 and A comes, then it will go to state 2, and what is the output? N again is observed. Then you are in state 2, again one more A comes, you are in state 2 only. Yes. So, what is that you will have to observe is, this is what is the thing, only when 2 A's consecutive A's come, then only y will be there, y is there, whether it is AA or BB it hardly matters, because that is how the problem is defined. So, this is how the Mealy machine works. So, output is associated with each input, whereas the Moore machine, the output is associated with each state. So, this is a very important one, and will transition table, if you look there, the same thing I have written it in the transition table form, and what is the output for each one. When the A is there, first A, it will go to 2 and it will output n. All this is whatever I have done on the board, the same thing has been written in the transition table form. So, now this is how, this is all what is the what is need to be covered in chapter 5. Chapter 5 is a very important one. You have you can expect a lot of questions from the chapter 5, because chapter 5 will consist of a lot of different types of methods are there. So, the problems will arise from the chapter 5 and you need to study thoroughly chapter 5, like I have already explained you how to write a deterministic finite automata, then also you have to how to write a non-deterministic one, how to convert from non-deterministic to deterministic. All this will be, this is there in chapter of minimization. So, they are all very important and you must practice that. Now, the next chapter is chapter 4. I have changed the order, so that it is makes more easy for you to understand. So, in this chapter effort is made to define the problem as languages to be decided. It is somewhat abstract. So, why problem should be associated as languages. So, that will be clear as you run through this subject. Define programs as state machine. This I have stated. So, a state machine, whether it is a DFA, NFA or whatever it is like a program. When you design for accepting AA or BB, then that state machine will act as a program for the particular language. Now, the whose input string and whose output is accept or reject. Now, the key ideas in this chapter 4 are decision procedures, non-determinism, function on languages. So, these are very important concepts. So, as you go to the higher classes. So, what is this decision procedure requires certain explanation. The decision procedures are one which definition, if you look at, it will have only yes or no. It is like your objective type of questions, yes or no type. So, you must ask why decision problems have been taken, why not a particular answer for a problem. See, basically the people have a notion that decision problems are easy, whereas finding an answer are difficult. No, it is not, it is only a notion. Actually, the decision problems are as hard as the problem of finding an answer. So, that is why decision problems are considered, so that it may look easier, but they are as good as any other harder problems which require answer. The decision procedure is an algorithm to solve a decision problem. So, we come to a very important concept. So, you can make a decision provided there is an algorithm. If there is no algorithm, no matter how, what kind of computer you have, what kind of language you have, what kind of facilities you have, it is of no use. First and the foremost is you must have an algorithm to, you must know with a paper and pencil, you must be able to compute it. Only when you are able to compute the answer using paper and pencil, then only you can submit it to a computer using some language. Only thing is it will do it faster, but if you do not know the method, procedure or the algorithm is not known, then no matter how much, what kind of computer you have, what kind of language you have for programming and all, it is of no use. So, finally, what is that what it is trying to impress is the algorithm is a very important part of computation. Now, a program whose result is a Boolean value, decision procedure yes or no, like the simple DFA is there, it will say accept, not accept. Okay. So, most of the machines will be of that type, accept, no, not accept. So, they will be decision procedures. In order to return to a Boolean value, a decision process must guarantee to halt on all inputs. Very, very important is one of the characteristic of algorithm is it must halt, no matter how much time it takes. But sometimes when you say no matter how much time it takes, means the time should be meaningful. I have given you a example already. Suppose the students exam is over, tabulation is done and all. So, the tabulation should be over say meaningfully within a month or 15 days, but suppose it takes 6 months, then that kind of program is useless, because we require results within 6 months or within 15 days or a month. So, the problem is not just it should halt also within a meaningful time, very important. So, the one of the very important characteristic is this one, it should halt. So, decision procedures are answers to the questions such as, is a string yes in language. See, for example, if you take a DFA, DFA will tell you whether the string is accepted or not accepted by going to a different. Now, given a machine, does it accept any string? Okay, these are all more philosophical questions that will be tackled. Given two machines, do they accept the same string? This is yes, you have done it in a indirect way. Suppose you are given two machines, two DFAs and one language, whether do they accept the same language? Suppose you want to do that, they may look different, the figure may look different, but when you reduce, we have minimization of a DFA, you minimize the first machine and also minimize the second machine, they will all be brought to a normalized form, then you know that whether they will be accepting the given language or not. So, if they look alike, then you know that they are the same machines drawn in different way. So, this is possible. Now, the next is, given a machine, is it the smallest machine that can do the job? Yes, again it is a minimization. So, we have tackled such problems wherein there were 3 states were there and we reduced it to 2. So, that is the minimum most wherein we had the concept of equivalence class. So, with that we are able to reduce the states of the DFA. The 3 things are important thing. Does there exist a decision? That means, it is as good as an algorithm. Is there an algorithm? You must have studied the design and analysis of algorithms, wherein you will see that the problem of traveling salesman problem, though the method is exists, but it is a question of exhaustive search. When you do an exhaustive search, it is going to take, it becomes intractable. That means, it will not be able to give, if the number of cities are more, it will not be able to give the answer in a meaningful time. So, if any decision procedure exists, find one. If it exists, find the most efficient one. Then this we have been doing it in the other classes. For example, if we say that the procedure is for sorting. Sorting, there are so many procedures or the algorithms are there. For example, quick sort is there, bubble sort is there, insertion sort is there, so many types of sorts are there, merge sort is there, but again you find which is the efficient one. Why we select quick sort? Because it is a most efficient one compared to bubble sort. The bubble sort has got a complexity of big O of n square, and that means it takes more time than the quick sort. Quick sort has got the complexity of big O of n log n. So, therefore, we find the most efficient one. For example, again to give another example, for example, you have binary search and linear search. You know that the binary search is efficient, it takes only a time big O of log n, whereas a linear search will take big O of n. So, therefore, the binary search is a efficient one. So, all our efforts in engineering will be to, when you find a method, you should be efficient. In computer science, when you say efficient, it should take less time and also less memory. So, decision procedures are programs. Any algorithm is a program and they must have 2 correctness properties. So, the program must be guaranteed to halt. If it does not halt, then you do not know what is going on. The answer must be correct. So, these two are the essential requirements of a program, which you have written many programs. If the even if it gives the correct, I mean it gives the answer quickly, but if it is not correct, then it is a worthless program. So, and if it goes in infinite loop, you do not know what is happening. So, these two are the very important requirement. Now, we will see some of the examples wherein you have already done these things in a different class. Then these are the thing for which we have algorithms. Then in the end we will see a problem wherein there is no algorithm for that. That means what? It does not halt. So, okay. So, for example, if you checking an even number, whether it is even, x is even, given that means you are given 2, 3 and all that, which is even, which is odd. So, if x by 2, that is integer division, this you will have to take this as a integer division, then into 2, if it is equal to 6, then it is a true, else it is written false. For example, if you take 3, you know that it is not even. So, when you do x by 2, then it is a integer division, 3 by 2 it will be 1, multiplied by 2 it is not equal to, it is 2, it is not equal to 3, therefore, 3 is not a even number, false. So, idea of giving this is that for all these simple things there are algorithms are there, therefore, you are able to compute them. For example, if x equal to 8 is there, then if you do x by 2, then it will result in 4, and if you multiply that by 2, then it will be equal to 8 and it is equal to original number, therefore, 8 is a even number. The idea of giving this is, as I told you, is only to say that these are all the algorithms which will halt and give you a correct answer. Okay, that is the two fundamental requirements. Checking for prime number. So, as you know, the prime number is 1, which is divisible by 1 and itself. Okay. So, now given a positive number, you input is a positive number will be there. So, negative number will not be there. Then for I becomes equal to 2 to ceiling, ceiling means that is up. Okay. I will explain that. Square root of x do. If x by I into I equal to x, then return false, then it is not a prime number. Example, if you take x equal to 7, then the ceiling of square root of 7 is 2.65. The ceiling of that is higher value, higher integer value. This is a float number, higher integer value is 3. So, then what you do, I equal to first iteration, I equal to 2, 7 by 2 is 3 into 2, 6, it is not equal to 7. So, it will go to next iteration, then 3, then 7 by 2, again it will be 2, 2 into 4, 4, it is not equal to 7. So, next iterations it will go, but there are no more iterations are there. You have already reached the end of the for loop. So, therefore, here there is a return true. That means to say that the 7 what you are doing is in effect, whether it is divisible by 2, it is divisible by 3, you are checking. It is not necessary to check divisible by 4. Okay. So, returns true, 7 is a prime number. So, this is the way to do it, and it always terminates and gives the correct answer, very important. So, this is another program, looks like algorithm, but it is not an algorithm. Okay. Checking for a program that halts on a particular input. So, as I have already explained sometime, so there is such a program cannot be written. That means, a program which takes that means halt. Okay. So, input is a arbitrary program, your own program say, then the output will be it is program halts, program does not halt. Only is program if it halts, then this output is possible. This output is never possible. If it does not halt, then there is no way to predict that this program after some time, after 1 hour, after 2 hours, after 1 day is going to halt. There is no way. So, if it halts only, then it can say yes, it can halt, it terminates, but if it does not halt, then there is no way of knowing that when it is going to halt. Okay. So, this output is, if the program does not terminate, for example, your while loop is there. So, that condition is never becomes false, while it is true it will go. So, it will continuously, it never becomes false means it will never come out of the while loop, then this output cannot come. So, forever it will be in the loop. So, this is what we have visualized. For this, so no program can be written for this, not that today it is not there. So, after another 10 years somebody will write it, no, it cannot be written at all. Okay. So, this is a very important program which you will have to understand that this is not an algorithm. So, if you just look at the other programs, if you see, you must compare it. A number, see, you had two outputs. Yes, the given number is prime, yes, true or false. You had clear cut, it terminates, not only it gave true and false, for any number it will give it, but whereas this will give only partially. That means, if it halts it will give yes, if it does not halt, then it will forever it will be looping. So, therefore, you have a program wherein this is an algorithm, this is whereas this is not an algorithm. Okay. A program which does not halt cannot be characterized as a algorithm. So, now determinism and non-determinism is very important. See, you have studied deterministic finite state machines and non-deterministic finite state machines. So, the deterministic means everything is the thing, you have no absolutely no ambiguity as to for a given input which state it will go, you have no ambiguity. But whereas in a non-deterministic machine you have seen on a particular input it can go to any number of states. So, that is non-determinism. So, for that there is a simple test is there. Consider your C language switch statement, something like that. So, you have number of actions are there, action 1, action 2, action n are there. So, you have seen that in the case of switch statement, if depending on the thing input or the what we are trying to test, it either it will take action 1, 2, 3 and all, most of the time it will be disjoint. So, if action 1 is there, action 2 and it can be made such that all the actions are also possible. So, that is where the way that depends on the way we have write the program. The observation on choose is a very important one. So, return some successful value if there is one. So, that means to say that all the actions are any one of them are true, all are true, then when it completes it will return 1. If there is no successful value, the choose will halt and return false. Okay. If there is no, all the things are completed and false, if all the actions halt and return false. Okay. And fails to halt, for example, one action is there, it goes on and on. So, that means one particular action fails to halt. Note that this has a potential to return, again same problem as you need to compare it with a halting problem. So, halting problem, just because it has not halted, it does not mean that it is not going to halt in next another 2 minutes. So, but you do not know. So, this is what is the note that this has a potential to return successful value, it may be taking more time. So, if you are using a concept like choose, then it is likely to be a non-deterministic one, and the definition comes like this. If a program does not use choose, then it is deterministic. If you do not have such concepts are not there, if a program includes choose, then it is non-deterministic. So, you will see that the programs like determining the prime and all will come in the first category, whereas halting problem or the problem of traveling salesman, they will all come in the second category, non-deterministic. So, now again we have some philosophical things which we have to understand, that is the functions on languages. I must remind you that the languages are sets. So, therefore, all the things which we have applied, union, intersection, difference and all that, complementation can be applied, that we have seen in already in chapter 2 we have seen. Now, we have some more functions are defined, and those functions whether they are closed or not. Okay, chop is a very simple function. It if all is all the odd length strings in L with their middle character chopped out. Okay, I will give an example for that. What is chop? So, it means if you take an odd numbered string, then the center thing will be a character, whichever is there, that will be removed and it will become even. Okay. So, that is then function first character determines the first character by looking at all the strings in the language. So, we will see some examples for this like this. See, for example, if the language consists of a power n, b power n, c power n, then if the length is 0, as you know, it is epsilon. So, there is no central character is not there. So, there is no question of applying chop. Now, if it is a power is 1, 2, 3, 1, 1, 1, then the string will be a, b, c. Then the center is chopped, then a, c it will become. So, now similarly, if n equal to 2, then a, b, b, c, c will be there. There is no central character is epsilon. So, it cannot be, even if you chop off it cannot be character. So, now when it comes to 3, you see that there is a central character. So, b is there, b is chopped off. So, that is what is the chop. So, why we are, I mean it may look very funny why we are doing this, but later on when you apply this to the infinite and finite languages, some very good results will come out of this. The example of first character, if phi is there, as you know, is an empty set, there are no characters in that, obviously nothing can come. So, if epsilon is there, then also there won't be, the epsilon is not it is only a null string. So, again phi will come. So, if you have a star, that means epsilon, a to the power of 3, a to the power of 4, etc., then the first character will be depending on the string. If it is a, then the first character will be a. If it is a, then the first character will be again a. First characters could be thing. Then if you have a power n, b power n, so the first characters could be depending on the what string you take, then it will be a to the power a star. That means, for example, this may not be very clear. So, for example, if you take a string a power n, b power n, a, b, b, if you take, the first characters will be a, or it could be a also, depending on the first characters is there. So, that is how the first characters is applied. That is why it is put a star, because it caters for all the sets here. Similarly, if you have a combination of A plus B star, then A star can be there, union B star can be there. So, there can be so many first characters could be there. Now, the effect of this first character or the chop is, what is you will have to understand is, if you take a language which is finite means it is not infinite, and if you take a language which is infinite. So, finite and infinite languages, I mean just to make it clear, I will write like this. Finite, for example, it could be a language, but we do not normally, this is finite, whereas L is equal to epsilon a star, a square, a cube, dot 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 infinity, then this is infinite language. So, we have finite language, we have infinite language. So, if you take the union of any two languages, that means two finite languages, suppose we call L1 L2, suppose L3 is also there. So, that is A and B finite. Okay. So, if you take any two finite languages L1 and L3, then it is going to be finite. So, for example, if you take L4 which is infinite, these are all infinite, epsilon b, b square, b cube and so on. These two are infinite languages. If you take the union of that, that also will be infinite. So, that is the meaning of saying. So, similarly, if you look at the results of this, what will be surprising is the intersection of finite will be finite, that is understandable. Okay. Now, intersection of infinite, if you are taking, it will not be this thing, it will be finite. So, because intersection of two, for example, if you intersection of this, if you take the intersection of L2 intersection L4, what is the common? Only this is common. Okay. So, therefore, it will be finite, it will not be infinite. Okay. That is what is the meaning. No. So, similarly, if you take chop, as you know, it will be the chop the center character. If it is a finite, then it will also be finite. Then if you take the first characters of finite, okay, and two things, then it will not be finite, it will not be no. So, you have to understand that the union of two infinite, if you take, it will be definitely be infinite. Then intersection, I have given an example wherein it is not infinite, it is finite, these two examples. Similarly, if you take chop, okay, then it will not be infinite, it will be finite. So, finite means it could be epsilon also, it could be empty string also. So, the first characters if you take, then it will also be infinite in case of both infinite and finite cases. Finite cases it cannot be infinite, it has to be few representative values will be there, therefore, it cannot be infinite. So, now finally, we have to have what is known as the language hierarchy. So, this is a very important byproduct of this subject. So, this you must concentrate. Then see what is that we have so far we have seen in the chapter 5 or chapter 1 to 5 is there are all finite state machines, and finite state machines accept regular languages. So, that is what you have done. So, next you are going to study what is push down automata, which is nothing but it accepts context free languages. Then you have Turing machine, which decidable languages. So, decidable means what, for which you can write an algorithm for which there is a answer yes and no, it will terminate. So, they are decidable languages. Now, for example, if you have semi-decidable language, Turing machine, semi-decidable language is halting problem of a program, that is semi-decidable. Why semi-decidable? Because if it halts, it will give yes, if it does not halt, it will have no output. So, therefore, it is semi-decidable. So, this is how the whole of the spectrum of formal languages is classified. Out of this, these two are of interest only for philosophical reasons, because we want to understand Turing machine, as I have told you, is equivalent to a digital computer, but Turing machine is a very simple machine. If there is a problem which a Turing machine cannot solve, then no matter whether you have a supercomputer or grid computers, whatever it is, that also will not be able to solve. If you want to solve anything, if you want to test whether there is an algorithm is there, it should first work in Turing machine. If it does not work, then there is no use in trying in any other powerful computer. So, this is the hierarchy, that is a byproduct of this subject, wherein you will be studying all these automata. All are automata. You have studied only this, the push down automata will be studied next, then the Turing machine finally you will be studying. So, all will have almost the same characteristics will be there, the states will be there, input will be there, and accept or reject concept will be there. That is common in all these automatas, that is the thing. Now, the importance of classification. So, why we need to classify? So, we have classified them into regular languages, then context free languages, decidable languages and all that. So, there is a meaning to this computational efficiency. As you know, which I have given you the example of a bubble sort and a quick sort. So, which is efficient, that only we want to use it. So, computational efficiency is the most important thing which we want to concentrate. So, finite state machines are linear with respect to input string. That means, if you it will take more time if the length of the input string increases, whereas the push down automata, it varies in a cubic way. As the length of the string varies, it is not linear, whereas a Turing machine is exponentially with respect to input string. That means, as you see that the complexity is gradually increasing, the linearity is not there. So, it is going to take less time, more time and still more time. So, that is how the computational efficiency is one of the important factor for why we study this is for computational efficiency. Then next is decidability, answer to the questions such as accept some string. Now, you see that in most of the finite state machines, it was very easy, and it is it minimal? I mean, the number of states are minimal. All these questions are possible in case of finite state machines. Is two finite state machines identical? It is possible. Okay. Now, only then as we enter into more complex automata, then only not all the things can be answered, only some of the above can be answered in with respect to a push down automata, and Turing machine none of them can be answered. So, this is where we want to understand the decidability problem, that is it gradually it goes down. Here everything is decided, some things cannot be decided, none of them can be decided. Then the third important aspect is clarity, the tools that enable analysis. One of the very important thing in computer programming is analysis. So, then can we analyze, can we have tools to analyze this finite state machine? Yes. PDA, yes, and Turing machine, none. So, you cannot have any analysis tools. So, now the summary of the module 1, I want to tell you what is important. Lot of things have been covered. Then what is important is, because this subject has been there for quite some years. So, from the background I can say that the construction of the finite state machines is very important. So, you must concentrate on that. Then how to write the non-deterministic finite state machines, very important. Then we have seen conversion of non-deterministic finite state machine to deterministic finite state machines with epsilon transition only is dealt in this book. So, I have given you both without epsilon transition, with epsilon transitions, they are important. Then the minimization of deterministic finite state machine, okay, Mealy-Nerod theorem and equivalence class and all are important. Then Moore and Mealy machines today we have dealt. Then finally, the classification of languages, which has classified into all the formal languages into 4 categories, that is also important. So, if you the homework what I want you to concentrate is all the problems related to chapter 2 and 5 are where most of the problems are there. So, you must work it out, and all the definitions are very important. Definitions, there is no substitute for definition. You must alphabet means the definition, string, finite state machine, that is 5 tuples and all that you need to. If it is a Moore machine, then it is has got 7 tuples are there, Mealy machine 6 tuples are there. So, definitions will have to be as given in the book only, you will have to do it. So, with this I conclude the that is the module 1 lectures. We had 7 lectures, and the next module will be taken up by Dr. Girjama, and afterwards Professor Deepa Garg, afterwards Dr. Ravi Shankar, then finally last module will be Dr. Sridhar. So, this is how this lecture series is going to go, and now if you have this complete module is completed, if you have any difficulties, please send a mail to this email. Thank you.